and they lead to ring formation. We're going to see molecules where the nucleophile and the leaving group are in the same molecule on different ends of it. And so that's going to lead to molecule reacting with itself. Let's start with epoxides. Epoxides are a function group we learned about for the second exam. We could take an alkene and react it with a per acid to make an epoxide. But we can actually make epoxides another way in the same molecule. Let's look at this particular molecule that I've drawn here. It has a chlorine group and an alcohol group kind of close by to one another. Chloride's the leaving group. The molecule is going to be a substrate at this position. This is secondary. But as this is written, this is a poor nucleophile. So this molecule is actually stable as written. But if we could convert this into a powerful nucleophile, this reaction will actually work. And so one thing we could do is we could react this with a base. Maybe sodium hydroxide. There's other bases we could use too. But what if we did an acid-base reaction here? Now actually we have a good nucleophile and good leaving group all in the same molecule. And so this can actually internally cyclize. The way this particular reaction works will require that we draw a chair conformation so we can understand exactly what's happening. So we're going to take this and put it in a chair conformation. These two groups are trans to one another. So chlorine is up and O minus is down. And we'll draw on the other hydrogens here that are relevant, like this. This is one possible conformation. It turns out this conformation is unreactive. We need this O minus to be able to attack at the backside of this carbon-chlorine bond for it to leave. If we ring flip this, chloride becomes axial, oxygen becomes axial. And from this particular conformation, O minus can actually attack. I won't ask you to do this on an exam. You could actually do this here on paper. You could just draw this mechanism internally, but I want us to see how this actually happened. For these electrons to find this backside location, we have to have this in a diaxial conformation. So the way it actually works, you could build it with a model to see for yourself, and when we do that, we get to an epoxide. The stereochemistry here is going to invert, and as we've seen before, this particular epoxide we would probably best draw at first glance with these groups down, but if you draw them up, it's equally okay. So epoxides are the first type of intramolecular SN2 reaction we're going to explore. This one clearly illustrates the effect of having nucleophile leaving group in the same exact molecule. We're now going to look at the effect of the ring size that we're forming and the speed of this reaction to get a better understanding of this concept or idea of intramolecular reactions, where both reaction components are within the same exact molecule. We're going to look at amines in this particular case, and we're going to start out with a series here. Let's look at intramolecular SN2 reactions, and these will be cyclization reactions. Okay, just in general, if we have an intramolecular SN2, it'll cause a cyclization. Intramolecular reactions in general are very fast, since both reactants are in the same molecule. For example, if we had a leaving group and a nucleophile in separate molecules, the rate of this type of reaction is a function of the concentration of the substrate and the concentration of the nucleophile for SN2 reactions. And this means that the higher the concentration is, the faster this reaction goes, because the reaction speed is dependent on these two things finding each other. And if they're at high concentration, then they find each other much faster and the rate goes up. If the leaving group and the nucleophile are in the same molecule, the kinetic equation is much different. It's no longer a function of these concentrations of one another. And so this type of scenario of these two finding each other is significantly faster. You probably didn't learn about this in general chemistry. You learned about these simple rate equations and different factors influencing how fast rate goes. But just imagine that these two things don't have to find each other in a big pot. They're a few angstroms apart from one another. They just have to collide with one another and it's over. So intramolecular reactions will be much faster due to this particular facet that the kinetics have changed drastically. The two things just have to find each other a few bonds away from another, not all over different flat locations in a flask. So we're going to use amines for this. We're going to draw a whole series of amines here. Let's draw an amine that has bromine in it with an ethyl group. Then we'll draw a propyl group, separating the two. Then we'll draw a butyl. We're just going to do a whole sequence of things here. So I have 4 carbons. And how far are we going to go today? 5 and 6 carbons will do. And I missed 5 in the middle here. That's unfortunate. Well, these things happen. So we'll just take our time. I'll slow down since I'm messing things up here a little bit for us. So we'll have 1, 2, 3, 4, 5 carbons. And then we'll have 6 carbons. To get these reactions to work, actually they're catalyzed with a little bit of sodium hydroxide. That's not really the important point here, but we're going to look at the products we make here as well as the rate constant, which was measured for these reactions, which is a small k. And this particular rate constant is going to allow us to at least have an appreciation for what rings are best to form in nature and in chemistry. So when we do this particular reaction under these conditions, we get a 3-membered ring. Here we would get a 4-membered ring. Here we get a 5-membered ring. 6. And 7. 7's the less fun one to draw. So just put a number 7 in it. So look at these products. You could draw the mechanisms yourself, see how these work. But just draw one of them here. It's like forming an epoxide in the first case, except this is the nitrogen version of it. There's an acid-base step that has to happen, and we get to these cyclic secondary amines. And the speed of these reactions is measured in terms of rate constant. So we're just going to see some relative numbers here. It's numbers you don't need to memorize, but 0.036, 0.0005, 30.0, 0.5, and 0.001. So 30 is the fastest, and we'll say that 0.05 is fast, and the other ones are a lot slower. We're going to talk a little bit about why this is. In general, in nature, forming 5 and 6 membered rings is very, very easy to do. So forming 5 and 6 membered rings in nature is very, very easy to do. You'll recall in your study of cycloalkanes, 5 and 6 membered rings were quite stable. 4 had lots of strain, 3 had lots of strain. So we get to 7, 8, 9, 10, these things get kind of bulky and wobbly and unruly. So forming 5 and 6 membered rings, these are stable compounds. They can form very fast. 4 membered ring is very, very unstable. 3 membered ring is also very unstable. But these two things, finding this location, is actually quite easy to do. But 3 membered rings and 4 membered rings result in some instability. 5 and 6 membered rings are very stable rings, and the nitrogen group is quite close, easy to find. As we start getting to 7 membered rings, or 8 membered rings, 9 membered rings, 10 membered rings, it just becomes a little bit more difficult for this nitrogen to kind of find out where to react. It just takes more time for it to find there. And so the speed of the reaction gets slower. So just want us to appreciate that we can form rings in lots of different organic chemical transformations. And just this particular slide allows us to emphasize this point that forming 5 and 6 membered rings will always be easy in science and chemistry. 4 membered rings have the challenge of strain, and 3 membered rings and 7 membered rings have the challenge that these two groups get harder and harder to find. From a practical point of view, we can't even make 9 or 10 membered rings easily. If we want to get to 10, 11, 12, we have to use very, very special techniques. We want to make 10 and 12 membered rings sometimes because there are very, very important medicines that contain these, but this type of technique doesn't work. But 5 and 6 membered rings are pervasive in nature. You open up any biology book, any chemistry book, you see these structures everywhere. And as you explore science further as young people, you'll find lots and lots of medicines, drugs, biomolecules with these 5 and 6 membered rings built into them. We're going to use this idea of intramolecular reaction for one more purpose today, and then we'll wrap up. Important things for us is this formation of cyclic amines as well as epoxides. Those are the important groups that we're talking about, but for our own edification, we're going to talk about